Let us start, sir. Yeah. Start, sir. शुरू करायचं.
हाँ चालू करो. चलो चलो.
Good afternoon to one and all participants. We have with us for today's session Dr. S.R. Sathe, sir, professor in the Department of Computer Science and Engineering, GNRT, Nagpur. He has more than 30 years of teaching experience, and also he has published several papers in SCI, Scopus, and Web of Science Journal. Sir has also published two books, one on operating system and the other one is on foundation of computer science. And his area of interest is parallel computing. So may I request Sathe sir to start a session on dependence analysis. So please, sir.
Okay. So good afternoon, all of you. So this time I am speaking remotely, unlike other times when I would have been there and talking with you. Although most of these participants may know me, but nevertheless, introduction was okay. So we will discuss, since this workshop is on parallel computing, right? What is the title of workshop? Parallel computing, right? So we will be discussing dependence analysis. Any topic on parallel computing is incomplete without the knowledge of dependence analysis. So you must know what is dependence. If two things are dependent, then they cannot be executed in parallel. Okay. Or if they are, the one process which is dependent on the other must execute after the first one has been executed. So therefore, dependency plays a very important role, and dependency, it is the dependency which prevents parallelization of computer programs. Okay. So why parallelization? The goal of parallel, I think I am audible to all the participants. If not,
yes,
please put in chat. If not, chat is open on my computer. So if there is any problem, you can just chat there. Okay. So that I can take corrective action. This is how I take the classes also. So this technology is not new to me. So many 50-60 classes have already been held. So somebody has said Dr. Tumbanath, right? Samantha has said yes, sir. So it means I am audible. Okay. The goal is to reduce the execution time. For achieving this goal, multiple processors or cores are used. So in the earlier last century, there are multiple processors were used for, that was called as a multiprocessing system for parallelization. Today, we have multiple cores on the same CPU chip. There are several cores. Okay, say 4 core, 8 core, 16 cores. And in fact, on the mobile computing, on our mobiles also, there are quad core processors. So using 4 cores, the execution time will be, we estimate that it should be 1/4 of the single core time. So speed up, which is a measure of how much you have parallelized, that is equal to 4 in this case, right? So not all programs can be parallelized. It is the sequential code. So if that part of the code which must be run sequentially prevents parallelization of your computer program, and that is governed by Amdahl's law, which says speed up is equal to 1 upon alpha plus 1 minus alpha by p. So if p is very large, then 1 minus alpha by p will be small. So it will be, speed up will be maximum you can go is 1 upon alpha, where alpha, for example, is 0.1. That is 10% of the program is to be executed is strictly sequentially. Then the speed up is limited to 10 only. Okay. So therefore, this Amdahl's law has also to be kept in mind, and you should have as much less sequential component of your code as much as possible. The application areas of parallel computing are nowadays too many. Just to name a few which are related to our computer science or scientific computing, we have linear algebra. So all sorts of matrix algorithms like matrix transformations, then Gauss-Seidel methods and all those which fall under this can be parallelized. Then spectral methods like Fourier transforms, which are heavily used in signal processing, they are also very important. Graph traversal techniques, dynamic programming, which is a very important optimization technique that can also be parallelized. Then with the advent of cryptography, so cryptography techniques can also be parallelized. So what the advantage of speed up is you can encrypt using a less amount of time, or if you are a cryptanalyst, then you can decrypt using a less amount of time. Okay, so these are the several areas I have listed, and apart from the machine learning, all the areas so can be parallelized using parallel techniques in parallel computing. So there are several techniques of parallelization. Bit level parallelism. So bit level parallelism is simply increase the bit word size. If you have a 8-bit CPU, make it 16-bit. Invent a 16-bit. If it is 16-bit, 32-bit. So on 8-bit machine, the 16-bit addition requires 2 instructions, 8-bit at a time. Whereas on only one instruction is required on a 16-bit machine. Okay. Instruction level parallelism, which means either instruction pipelining or very large instruction word. So if the instruction word is very large, then you can what you can do is you can put several instructions in the same instruction. So okay, one instruction containing a large number of instructions. That is instruction level parallelism. Data parallelism is where it emphasizes the distributed or parallelized nature of the data. That is, the parallelization is now embedded in data itself. That is data parallelism. So we have two terms in parallel computing: data parallelism, task parallelism. So data parallelism is where parallelization is in data. So systolic array is one architecture which exploits data parallelism. And task parallelism is for multi-processors machine or multi-core machines. Okay, where an application is split into several tasks and which are independently executed on the several processors. Matrix addition with two processors. For example, if you have, then divide the matrix into two parts. One part handles the one part of the matrix addition. The second part handles the second part. There is no dependency here. So therefore, both this can do simultaneously, giving a speed up of 2. Okay. And the task parallelism focuses on the distribution of tasks. So in this, application must be divided into sub-programs or threads that cooperate to deliver the desired functionality. So these are the just a few techniques of parallelism which I have listed. So something is parallel if there is certain level of independence in the order of operations. In other words, it doesn't matter in what order those operations are performed. Okay. So we have a certain need. For example, one example is given: A is equal to B plus C plus D plus C. So how will sequential processing go? A is equal to B plus C. So A is a variable which is now holding the value of B plus. To it add D, to it add E. So you get on the left hand side serial processing is indicated. So that is A is equal to B plus C, A is equal to A plus D, and A is equal to A plus C. So A will hold B plus C plus D plus C. However, if you have parallel processing and you can have two threads, you can have a T1 holding the value of B, computing the value of B plus C. Simultaneously, T2 is computing D plus C. Okay. And thread 0 then gets the values of T1 and T2 and simply computes T1 is equal to T1 plus T2. So with this, same thing which required 3 instructions can be computed using 2 instructions only. Okay, so giving rise to speed up. Okay. So these are the two references that with respect to which this lecture is the material in the lecture is taken from. So there is Utpal Banerjee's, which is an old book, Dependence Analysis for Supercomputing and Loop Transformations for Restructuring Compilers Reformations. So these are all old books. I don't know whether they are available in the market. Try to search in Amazon and get it. Hello.
బొగ్గలోకి పెట్టాలి.
Hello, Rajesh, काही क्वेश्चन विचारताय का?
Any question from participant side?
Oh.
Hello, madam, any question?
I am hearing something.
No.
No. ठीक है.
No, sir, no any question.
Then ask them to mute their mic. Please mute your mic because wait, please. Please mute your mic. Okay. I thought somebody was asking question. Maybe he has accidentally put his mic on. Okay. So lexicographic order. Cartesian. Consider the Cartesian product z to the power m, where z is the set of all integers. So it is a m vector, that is a vector of size m. Each element of this vector is integer. The elements of z to the power m will be referred to as integer vectors of size m, or integer m vectors, or vectors in the z to the power m. So for example, one of the vectors will be 1, 2, 3, 4, etc. Okay. So that is, so we refer to it as a z to the power m or m vector. Okay. If the leading element of a non-zero vector is IL, then the positive integer L between 1 and m is called the level of I and is denoted by level F. So for this there is an example. So we find out the leading element of the vector. If it is IL, then the positive integer, and that is a non-zero. Okay. So for example, and a vector I is lexicographically positive or negative if its leading element is positive or negative. So consider the vector 1, minus 10, 0 to minus 32, and 0, 0, 2. These are positive because you start from left to right. The first, when I put the mouse cursor, is it visible, mouse cursor?
Yes, sir, it is visible. Yeah.
So I can use mouse cursors for for pointing. Okay. So 1, minus 10, 0. Then the second vector is 0 to minus 32. So second vector is also positive because the first non-zero entry is 2, which is positive. In the third 0, 0, 2, the first non-zero entry is 2 and it is positive. So these are all positive vectors. We call 1 minus 10, 0 to minus 32 and 0, 0, 2 as positive vectors. Consider the vector minus 120, 0 minus 2 and 0, 0 minus 1. The first non-zero entry is negative and therefore these vectors are negative. Okay? These vectors are negative vectors. A non-negative vector is either the zero vector or a positive. Okay, a vector which is non-negative means either zero or positive. Strictly not. Can you please elaborate for what purpose? That is coming up for dependence analysis. This lexicographic ordering that we are seeing is coming for is being used in dependence analysis. Okay, so if I were to just tell you right now, if these are the dependence vector, then positive vectors are permitted, non-zero vectors are permitted for dependence. If the dependence is negative, then it is wrong. It is going to give a very wrong result. Okay, so that we can also do.
Yes, sir.
A non-negative.
Yes, sir. Yeah, sorry to disturb you.
Okay.
But purpose of dependent analysis, I am pretty new to this particular area of distributed or parallel computing. So if you can just elaborate on the purpose of dependence analysis first, and then we can let us.
Wait up. Right now, I have not even started dependence analysis.
Okay.
When we will come to that particular program, then there are several programs coming up. In those programs, I can tell you what is the. So right now, these are all the definitions which are required for dependence analysis. Okay. So, no problem, and you can always ask questions afterwards also. A non-negative vector is either the zero vector or a positive vector. The sign of an integer I is denoted by SIGI, and where sin I equal to 1 if I is positive, sin I equal to minus 1 is I is negative. And if, for example, sin of plus 5 is 1, So, minus 5 is minus 1 and 0 is having a 0 sign. Okay. Now here we will start the concept of dependence analysis. The goal is to maximize CPU utilization. Okay. To ensure this, the compiler must discover the underlying dependence structure of the program. Okay, what is the dependence structure? Suppose a point in execution is dependent on some other point. It is using the value which is being computed earlier. Then this point has to wait until the first point has finished its execution. Okay. So this is determined by way of different actions in the program reference, read write of memory, and by the control structure of the code. So we have two types of dependence: control dependence analysis and data dependence analysis. So in this lecture, we will focus more on data dependence analysis. Control dependence analysis, in fact, in literature also, there is not much focus on control dependence analysis. The focus is more on data dependence analysis. Okay. For example, I'll just mention in one slide what is control. A statement S2 is control dependent on S1. That is, we write S1 delta C S2. That is, it is read as S2 is dependent on S1, not S1 dependent on S2. If and only if S2's execution is conditionally guarded by S1. Okay. So, for example, we have statement S1. If X greater than 2, go to L1. L1 is at S3 and S2 is Y equal to 3. Okay, so S2 is dependent on S1. Why? S2 runs only if the predicate in S1 is false. Because if S greater than 2 is true, then it jumps to L1 and S2 is not executed. So S2 is dependent, control dependent because of this if condition. It is control dependent on S1. Okay. So this is the only slide for control dependency. As I said, we will be discussing heavily data dependence analysis. And a lot of mathematics is also there, so be prepared. So what is a dependence definition? For two statements S and T, we have T depends on S. Okay, T it is read as delta T is read as ulta T depends on S. If there is an instance Si of S, right, and an instance Tj of T, and there is exist a memory location such that so both Si and Tj reference M. Okay, so that is one of the Si is to be both Si, they are referring to the same location. S is writing the variable and say T is reading the variable. Then S must execute before T. Okay, so Si is to be executed before Tj in L. And during execution of L, M is not written in the time period from the end of execution of Si and the beginning of execution of Tj. And this SIT need not be listed. That is, it can be same statement. So there is one. So since somebody has raised this query, where it is useful, I'll just take an example and again go back several 2-3 slides back. So consider this double loop. Consider this double loop. Okay. So in this case, let I1 be a value of 2 and I2 has a value of 2. So S bracket 2 2 means S with a value of I1 2 and I2 2 writes A3 2. For example, you substitute I1 equal to 2 here, you get I1 plus 1, that is 3. So 3 comma 2. So S22 writes 3 2 and at I1 equal to 3, I2 equal to 1, substituting the in the statement for T, T31 reads A32 because I1 is 3 and I2 is 1. Okay. So now focus on this part. You will notice that this iteration with I1 equal to 2 will definitely come earlier than I1 equal to 3. Right? So S, the statement S is writing first and statement T is reading later. So can we have, suppose you parallelize this program, can you have T31 reading first? Lecture कौन चाहिए? हाँ दे दो 3 मिल रहा है क्या? हाँ लाओ, just a minute. Okay, so therefore we notice that S cannot execute, S22 cannot, T31 cannot first execute, because otherwise it will end up reading old value of A32. So you must have the first S statement writing A32 and T31 then reading that value. Okay, so I'll just go back a few slides. We are here. So S delta, and we write small f, right, superscript. T, Si writes M and Tj reads M. That is precisely what we saw right now. So first the statement is, this Si means the index variables, right? S stands for statement, and bracket I stands for the value of the index variable. So Si writes M and Tj then reads M. So it is a read after a write. So it is a flow dependence. It is a read after write, and therefore it is flow dependent. S delta A T, Si reads M and Tj writes M. Okay. So it is a write after read. Okay. It is a write after read. And so this is anti. So what in this case, Si is reading first the value of memory location. Notice that this M and this M are same. They are sharing a variable. So dependency comes only when there is a sharing. Okay. Only when there is sharing. If there is no dependence. So for example, one question is, suppose we have a critical section and all of them are readers, right? Then there is no critical section problem. We have to, all of the readers can read the variables simultaneously. The problem comes only when there is write. So then we have read after write after read, or write. All permutations. Okay. So if the write happens first and then the read takes place, it is read after write, flow dependent. If read takes place first and write happens later, then it is write after read. Okay. So that is anti-dependence. So the variable is first read and then return. If there are two writes, now that is written as S delta small o as a superscript T. T is output dependent on S. So Si writes M and Tj reads M. So that is write after write. Will this, according to you, is it proper to call this as dependence, or there is no dependence? What will be the problem? If somebody can ask, if both are right, what is the problem? There is no dependence. So what will be the problem if you allow, if you alter the sequence of execution? What will happen? Anybody in chat, can you put the reason? Or you can speak also. So somebody who wants to participate can speak also. There is no issue. So question that I'm asking is,
Data inconsistency.
Data inconsistency, right? So for example, can you anybody elaborate? So for example, S is writing I equal to 7, and this fellow T is writing 10. So the final result will depend on the order, right? So in the sequential execution, if 7 is written and then 10 is written, in parallel execution also, you should have 7 written first and 10 written later. The final value should be 10. If you reverse the order, suppose I is written with a value of 10 first, and then I is written by a value of 7, the final value will be 7, not 10. That is the problem. Okay. So write after write is also contributing to what is known as output dependence. So these are the three dependencies in sequential execution of programs. Right, when you parallelize a sequential program. So we said S delta T. T depends on S. Dependence on T on S is a set of all pairs Si, Tj that satisfy the previous definitions. There can, on the same program you can have flow dependence. In the same program you can have anti-dependence. In the same program you can have output dependence. I less than j. Iteration Hj depends on iteration Hi. Right. So we say a distance vector, that is d is equal to j minus I. If at iteration I equal to 2, the value is written, and at iteration 3, the value is read. Right? What is so I is equal to 2, j is equal to 3. Next iteration, the value is read. Then the distance vector corresponding to this will be 3 minus 2, 1. Right? The sign direction vector is sign of this dependence vector. That's why I took initially this sign function. Okay, the distance was say equal to 1, so sign of this will be equal to positive, which is 1. Okay, suppose the distance vector is 5. Okay, we are assuming only one nest, there is only one loop. So distance vector is 5, direction vector will be 1 because sign of 5 is 1. And level of dependence is level D, that is at which index variable the dependence exists. Okay, that is called as the dependence level. Suppose there are two nest of loops. There is a nest, one nest which is I cannot write anything, right? If I want to write something, I can have my tablet. If I want to explain, is it clear or not? If it is not clear, then I can explain through a tablet. So dependence level, so if there are two nest of loop for I is equal to say 0 to 100, the next level is j equal to 0 to 100, and the dependence level tells you if the first entry of the direction vector is positive, then it is at level I, that is level 1. Okay. Since I is less than equal to j, distance vector must always be lexicographically non-negative. Okay. The distance vector will always be lexicographically non-negative. Either it is 0 or it is positive. And the meaning of this lexicographic was already told to you. Okay. That's why these two mathematical terms were taken initially. So if t depends on s at level L, 1 less than equal to L, less than equal to L, we say that dependence on t on s is carried by loop L. It is called as loop carried dependence. Okay. And dependence on t on s is loop independent if it is not carried by loop L, that is level is equal to m. So now comes same program. In this case, s and t are the statements. Okay. So I write S22 writes A32, and at iteration I outer loop 3 and inner loop 1, T31 reads A32. So it is a read after write, RAW. It is a flow dependence. So T is flow dependent on S. Okay. S22 write is executed before A31. Okay. So T is flow dependent on S, that is S delta F T. And the dependence is at level 1. Okay, what is the dependence vector in this case? You subtract 3 minus 2, that is 1, and 1 minus 2, that is minus 1. Okay, so you get a dependence vector as 1 comma minus 1, which is our direction vector is 1 comma minus 1. So it is a positive dependence vector. And so here I can explain the level. So the first entry which is non-zero, non-negative, that is 1, and it is at level 1. This is level 1, this is level 2. Counting is from left to right. Okay. This one refers to the outermost level, that is I1 loop, and this I-1 refers to the innermost, that is I2. Okay. So level 1. So this is the read after write. So any questions on this? So I think this answers the query that was raised. Okay. Dependence between for array B. Now there are multiple dependencies here. You are not restricted to only this. So as for example is reading I1, I2. B array is being read, and in statement T the B array is written. So let us see. At I1 equal to 2, I2 equal to 2, S22 reads B22. Right? And at I1 equal to 2, I2 equal to 1, T21 writes B2. Okay. So in this case, T21 write is executed before write. So in this case, S is flow dependent on T. S is flow dependent on T. T first writes and S reads. Okay. So S is flow dependent on T, and now the dependence vector is 2 minus 2 0 and 2 minus 1 1. Okay. So dependence with respect to this is at level 2. Direction vector is 0, 1 and dependence is at level 2. So in this there is a level dependence at level 1 also, there is a dependence at level 2 also. Now again T and U are, there are another two statements T and U. Let us analyze them. At I1 equal to 2, I2 equal to 2, T22 writes B23 because on the left it appears on the left hand side. And at I1 equal to 2, I2 equal to 2, U22 reads B23. Okay. So now what about the dependence vector? It is simply on the same iteration it is happening, dependence. First writes, then the second one reads, because the indices are exactly same, I1, I2 plus 1 in both the cases. So, but now the dependence vector is 0, 0. The direction vector is 0, 0. So there is no dependence across loop iterations. Okay. So, but it is within the code. So in the physical code, U is coming after T, physically written after T, and therefore U is flow dependent on this. Right? So T is executed before U. So dependence vector is 0, 0, direction vector is 0, 0, and then we say level is 3, which is one more than the total number of loops. Right? So there is a no loop carried dependence between T and U. No loop carried dependence. It is by way of the how you have written the program that is determining. So you cannot split this between T and U. You cannot draw a horizontal line, and the upper part will go to some processor, and the lower part will go to another processor, because now they are themselves dependent, T and U. Oh, sorry. Okay. So aim of dependence analysis is to gather useful information about the underlying dependence. You must know what is the underlying structure of the program before you parallelize this program. Structure of a program and present it in a suitable form. Okay, so why is dependence analysis necessary? Because using OpenMP, have you covered OpenMP in this workshop, Rajesh? Any participant can also answer. If OpenMP is not covered, then it may be difficult for you to understand. No, OpenMP is not covered till today. So OpenMP is a API for very useful for parallelization on multi-core architecture. Okay. So if you are using OpenMP and you are attempting parallelization of programs, it is not easy if you don't know the dependence analysis. Okay. So dependence analysis is to be done by the programmer, and then OpenMP constructs can be used for parallelization of that program. That is how it is done, and therefore the theoretical knowledge of dependence analysis is very important. So how to maximize extraction of parallelism from a sequential program, that is very, very important. Okay. So the aim of dependence analysis is to gather useful information about the underlying dependence and the structure of a program and present it in a suitable form. So consider the program segment given below. That is, L1 is a loop. I1 runs from 10 to 100 in steps of 3. L2 runs I2 from 50 to 5 in steps of -2. And there are statements like x2 I1 minus 1. Now I am assuming some complicated program, comma I1 plus I2. And t is x 3I2 plus 1, 2I1 plus 2. Okay. So let the value of capital I1 be small I1, I2 is small I2. So therefore S is written replacing capital I1 and I2 by I1 small I1 I2 respectively. Similarly, for statement T I am using J1 J2 at iteration J1 J2. Okay. Suppose there is a dependence between these two, right? So there can be a dependence between these two with respect to iteration I1 I2 and J1 J2 if both x that I have written refer to the same memory location. They will refer to the same memory location if their first and second indices match perfectly. Therefore, 2I1 minus 1 should be equal to 3J2 plus 1. Okay. And I1 plus I2, that is second index, must be equal to 2J1 plus I1 plus I2 should be equal to 2J1 plus 2. So you have to solve these equations. Okay, so 2I1 minus 3J2 equal to 2, just transforming here and there, and I1 minus 2J1 plus I2 equal to 2. So find the values of I1, I2, J1, J2 such that these two constraints are satisfied, two conditions, equalities are satisfied. What are the constraints on I1, J1, I2, J2? I1 must be from 10 to 100 and I2 must be from 50 to 6. So if you get a solution which is say for I1 it is 11, then there is not a dependence because I1 is not going to take that value. Mathematically you will solve it, but meaning of that will be there is no dependence because that iteration is not being I1 does not use that value at all. Okay, so this is how we have to solve these equations if we want to find out whether there exists a dependence between two statements. Now coming to loop normalization. In this case, we saw that the steps were 3 and -2, which makes it difficult to analyze the programs. Okay. First, the increment was 3 plus 3, and in the second, it was -2. Okay. So, therefore we study what is known as loop normalization. So loop normalization is the process of standardizing the loop iterations from 0 to 0, 1, 2 in the order of sequential execution. Okay, this process, that is, my loop iterations will always start from 0 in steps of 1. That is called as loop normalization. So therefore we introduce a new variable for each loop. We introduce a new variable for each loop. So index and what we study is index and iteration spaces. Okay, index space is what is in your program. This the values of I1, I2, they form a part of the index space. And iteration space means after you convert it into range from 0 to 1, 0 to something, 0, 1, 2, like that. That is iteration space. Okay. So again, so when loops do not have unit strides, two spaces are both finite subset of z to the power n. M is the number of loops in the nest of loops, and z to the power n is a set of integer m. Okay, a single do loop L of the form L I equal to p comma q comma theta hi. I is the index variable, p is the initial value of this variable, q is the final value, theta is the stride. In this case, the first loop stride is 3 and p is 10, q is 100. In the second case, p is 50, q is 5 and stride is -2. Okay. So this is the this is the standard form of the loop that we are using. HI is the sequence of assignment statements. This HI stands for some assignment statement in the body of the loop. So index values are nothing but index points of the loops. That is the values of the index variables I, index variable I, and index space of the loop is the set of index points. Okay. So index points and index space. So index space is a vector of or a set of all points, set of all index points. Okay. So an integer I is an index value of the loop L if I minus p by theta is an integer. Very clear. Okay. I minus p. For example, in this loop we want to check. We want to check whether I1 takes a value of 20 or not. Suppose in this program I want to check whether I1 takes a value of 20 or not. So what do? It is running in steps of 3. So 20 minus 10 is 10, 10 by 3. It is not an integer. So I1 will not take a value of 20 because it will steps of 3, 10, 13, 16, 19 and then it will go to 22. Okay. Suppose I want to check for 22. Right, 22 minus 10, 12. Okay, and 12 by 3 is 4, integer. So I1 takes a value 22. So that is what is written here. Right. So I takes the sequence of values p if I minus p by theta is an integer. So I the index value of the loop I is an index value of the loop L if I minus p by theta is an integer. And 0 must be less than equal to I minus p by theta, less than equal to final value is q minus p by theta. So this is where I have normalized the loop. Okay. So I take the sequence of values p plus theta, p plus 2 theta, p plus 3 theta, etc. I lies between p and q if theta greater than 0. Okay. Therefore, I can divide p by theta less than I by theta less than equal to q by theta. Therefore, 0 less than and subtracting p by theta from each of these quantities, 0 less than equal to I minus p by theta less than equal to q minus q with theta greater than 0. So I introduce a new index variable I caret. So I caret is equal to I minus p by theta. Okay. Or conversely, theta you take on the left hand side. I is equal to p plus I caret theta. Okay. So we have a new iteration variable I caret. Right. The final value of I minus p by theta. So final value of this will be q minus p by theta. So I have transformed the index space into an iteration space. And I have introduced a new iteration variable I caret. So 0 less than equal to I caret less than equal to q caret. Okay. And the final value q caret is lower of q minus p by theta. Lower of q minus p by. Okay, that is the file. So what we do is take a list of loops and normalize this. Then it is very easy to work in this iteration space rather than index space. Okay. So this loop that is written here gets transformed to the loop that is written at the bottom. 0 to q bar in steps of 1. Theta becomes equal to 1. And of course, h will also, the number statements that you have will also be transformed in terms of iteration area. Okay. So we have an example. I is equal to 120 to 10 in steps of -3. Okay. It is going in the reverse direction. It starts from higher value and goes to 10 in steps of -3. So 120 greater than I greater than equal to 10. Introduce I is equal to 120 minus I is equal to P plus I caret theta. Theta is -3. So 120 greater than equal to 120 minus 3 I caret greater than equal to 10. Okay. So we have 0 less than equal to I caret less than equal to Q caret. So even if this stride is negative, notice that our iteration space is going in the positive direction, which is very great advantage. So Q caret is equal to 120 minus 10 upon 3, whatever is it is a floor value of that. Okay, it is floor value. Okay, so we have studied going from index space to iteration space. Okay, stride becomes 1 and it always goes on increasing from 0 onwards, 0, 1, 2, 3 like. We say a vector I is less than vector j and there is a small subscript k if in these two vectors I1 is j1 equal to j1, I2 equal to j2, but at ik is less than jk. So vector I is less than vector j at k if the kth entry is of I is less than jth entry of k. Previous entries to this are all equal. Okay, and I less than equal to j k means either I less than equal to j at k or I equal to j. Okay, two vectors are equal if their all entries are equal. 1, 1, 1 and the other vector is also 1, 1, 1, so they are equal. Okay, so this is one more mathematical definition. So single loop with an arbitrary stride can be written as an equivalent to a unit stride. That is what we have seen. SI is the instance of statement S determined by an index point I, and Tj is the instance of statement T determined by an index point J. And now the distance from SI to Tj is J caret minus I caret. I am now talking of iteration space, that is iteration points instead of index points, where I caret and J caret are the iteration points corresponding to index points I and J. Okay. So we have a next, we have a for loop. So this, I think this I'll just go quickly because this is slightly repetition. So SI is executed before Tj if distance vector is greater than 0 or distance vector is 0 and S comes before T in the physical ordering of the statements in the actual program. Physical location in the file, that is. There is a file in which these statements are located, in which S is coming first and T is. So when you sequentially execute, you always execute from top to bottom. You don't go from bottom to top, right? So therefore, S will be executed first and T will be executed later. So any questions till now? If there are questions, you can ask. T depends on S. is written as this delta t, and we have also seen flow, NT, and output. Now, what is a transitive closure delta bar of delta? It is a relation of, right? It is a relation of indirect dependence. Right? Indirect dependence means, see, there are statements S1 to Sn, and if there is a directed path from S to T, right? So there is a sequence of statements S1, S1 delta S2, delta S3, delta Sn minus 1, delta Sn. So S1, the first statement S is S1 and last statement is Sn equal to T. Then, so what effectively I am trying to say is S2 depends on S1, S3 depends on S2. So indirectly S3 is dependent on S1 by transitivity. Okay, by transitivity. Okay, you must be knowing the transitive relation, right? If A less than B, B less than C, A less than C, that is transitive relation. Okay, then if a statement T depends on a statement S in the loop L, then each dependence distance satisfies D greater than equal to 0. Greater than equal to 0. The equality D equal to 0 is possible only if S less than T. S less than T indicates S is physically located in the file before T. So I have some list of some for loop. So here there are T depends on S. Why? T depends on S. Okay. So what you can do is you can just expand this like this and solve it. So I will skip this part. Okay, we already done it. For want of time, I will just come to the dependence problem. Okay, because in this lecture I have proposed to cover GCD test and Banerjee's inequality test. Okay, so we have dependence problem. Consider the model L and two statements. Model loop L and two statements assigned to T in its body. Let U be a variable of S and V a variable of T. Determine whether U and V cause a dependence between T and S. That is what is under consideration. Okay. U is X Fi and V is X Gi. Fi means some function of index variable I, and Gi means some function of index variable I. Okay. When S is less than T, U is an output variable of S and V is an input variable of T. That is, S writes U and V reads it, something like that. Okay. So this, it looks like this. X Fi and at T it is ready. If there is a dependence between S and T, there is a memory location M that is referenced by both Si and Tg. Okay. So f of I must be equal to G of J. Okay. So this is a dependence equation in terms of index values. Okay. I minus p by theta is an integer, 0 less than I minus theta, and j minus p by theta is an integer. So dependence equation in terms of index values is like this. Dependence equation in terms of iteration variables will be f. Now we have said that if I is index variable, I is equal to p plus theta I. So therefore, if I write f p plus theta I caret must be equal to p plus theta j caret. Okay, in terms of f of I is equal to g of j is written as p plus theta I caret is equal to g of p plus theta j caret in terms of iteration variables, and the value this gives the bounds of I caret and j caret. It start from 0, ends at q caret. If I caret less than j caret, then t depends on s. That is, in I caret the variable is written first and say j caret reads it later on. If I caret is greater than j caret, if I caret is greater than j caret, then at j it is at t the variable is written and then later on s reads it. Then we get s depends on t. If I caret equal to j caret and s is coming before t, then t is dependent on s. If S is coming after T, then S is dependent on T. So take an example. I is equal to 1 to 100 in steps of 2. So P is equal to 1, Q is equal to 100, theta is equal to 2. Again, P is equal to 1, Q is equal to 100, theta equal to 2. F of I is 2i and G of I is 3i plus 1. We want to know whether there is a dependence between this. That is, there are two iterations which are referring to same memory variable. That is f of p plus theta I caret minus g of p plus theta I j caret equal to 0. So 2 into p plus theta f is, what is f? F is 2i. F is 2i and g is 3i plus 1. So 2 into bracket p plus theta I caret minus 3 into p plus theta j caret minus 1 equal to 0. So simplifying this, you get this equation 4i caret minus 6j caret equal to 2. And what is q caret? Q minus p by theta with a floor value which is 49. So I caret and j caret, their bounds are from 0 to 49. So what is the one solution to this? 2, 1. Take I caret equal to 2 and j caret equal to 1. So it is 8 minus 6. Then another solution is I caret equal to 5, j caret equal to 3. So it is 20 minus 18, 2. So the values of the I caret, j caret are given here. 2, 1, 5, 3, 8, 5. Therefore, I caret is greater than j caret. Therefore, S depends on T. We have established that S depends on T. And these index values, iteration values are occurring here because they are within the range of 0 to 49. Now we write the loop like this. In this case, now the equation becomes 6i caret minus 2i caret 2j caret equal to 0. Right? 6i caret minus 2j caret equal to 0. After simplification, after putting the values. Okay. Because P is 1, Q is 100 and theta is 2. So 3p plus theta j I caret minus 2 p plus theta j caret minus 1 equal to 0. So simplification gives this. Now the solution will be 1, 3, 2, 6, 3, 9, 4, 12 like that. Okay, these are the values which satisfy 6i minus 2j equal to 0. Okay, 6i minus 2j equal to 0. So in this case, I caret is less than j caret. Therefore, T depends on S. Therefore, T depends on S. So this Euclidean algorithm is also required, but I am skipping this Euclidean algorithm that is used to find a solution to. So if there are two variables, two integers S and T, and two integers A and B, okay, then this has SA plus TB equal to GCD of AB has a integer solution. If the right hand side is not multiple of GCD, it is not a solution. Okay, so this we can find out from any cryptography books also will give that. So those who are teaching cryptography will know it, or it is also given in any discrete mathematics book. Extended Euclid's algorithm. So why it is required? I will, because otherwise a lot of time will be consumed in that explaining that method itself. Solution to the linear problem. Let A, B, C be integers such that A and B are not both 0. And let G be equal to GCD AB. The linear Diophantine equation AX minus BY equal to C. Diophantine equation means an equation whose solutions are integer. We want the solutions to be integers. It is a very important problem in mathematics. AX minus BY equal to C has a solution if and only if G divides C. Okay. What is G? G is the GCD of the coefficients. Right? Coefficients of X is A and coefficient of Y is B. They are GCD. If that divides C, then there is a solution. Right? And this solution is found using extended Euclid's algorithm. That is precisely what why that procedure is there in the slides. When a solution exists, the general solution is given by s comma y equal to cx0 by g plus bt by g, cy0 by g plus at by g, where t is an arbitrary integer. You substitute t equal to 0, you get one solution. Substitute t equal to 5, another solution. Substitute t equal to 2, another. So infinitely many solutions. Okay? And x0, y0 is a pair of integers. They are not arbitrary, such that g is equal to this GCD is equal to ax0 minus by. Okay. Now comes the first test, that is the GCD test. GCD test. If a variable xai plus a0 of a statement s and a variable xbi plus b0 of a statement t cause a dependence between s and t in the loop L, then the integer b0 minus a0 plus bp minus ap is an integral multiple of the integer theta into GCD. If this integral multiple condition is satisfied, then there may exist a dependence. If it is not satisfied, no dependence. Okay. So if the GCD test is satisfied, so let me come to that. So coming to the iteration variables, a times p plus theta I caret plus p a0, because the function f is ai plus a0, but I is p plus theta I caret. So substituting this value, you get a theta I caret minus b theta j caret is equal to b0 minus a0 plus b. But this has the GCD of the left hand side of the coefficients is, what is the GCD of a theta comma b theta? Theta into GCD of ab. So if this will have an integer solution, like whatever I am now rounding off here, this if will have an integer solution only if GCD of a theta comma b theta divides the right hand side, right? Or this is a theta into GCD of a comma b divides the right hand side. Then only there is a dependence. So consider the GCD test for this loop. P is equal to 10, Q is equal to 200, theta is equal to 5. A is 7, A0 is 2, B is 3, and B0 is 70. So what is the GCD of AB? They say GCD of 73 is equal to 1. Therefore, theta dot GCD AB is equal to 5. Theta is 5 and GCD of AB is equal to 4. GCD of AB is 1, so therefore 5. So what is C0 is B0 minus A0 plus B minus A into P. B0 minus A0 is 16. Right, 16 plus B minus A. What is B minus A? B minus A is minus 4, minus 40 plus 6. I think it is turning out to be minus 25. You can verify at home. So C0 is an integer multiple of theta GCD because 5 divides minus 25. Therefore, the GCD test passes. Since the GCD test is passed, there may be a dependence between S and T. Now again, we are not guaranteed. But if the GCD test does not succeed, then there is definitely not a dependence. If the GCD test succeeds, then there may or may not be dependence. Why? Can anybody tell? If the GCD test succeeds, that is, the left hand side divides, theta into GCD AB divides the right hand side, then we say there may be dependence. So why there may not be dependence? Huh? Even if it divides, there may not be dependence because the integer values which are causing dependence may be outside the loop bounds. Okay. So if those integer values for which there is a dependence are outside the loop bounds, then there will not be dependence. Okay. So disadvantage of this are ignores loop bounds, which leads to false dependence. When there is no dependency, we are forced to assume dependency. But therefore, GCD test is just applied first. If it does not succeed, there is no question of any dependency. When the later part analysis is not required at all. Okay. It does not provide any information regarding distance or direction vector, and GCD is often one which ends up being very conservative. अगर GCD 1 आ गया, तो क्या it is going to divide any integer? Okay, so we will assume that there is a dependence when there may not be a dependence, and therefore there is a method of bounds. Therefore, we have a method of bounds. What does it say? The dependence equation I have written: a theta I caret minus b theta j caret is equal to right hand side in the form ai caret minus b j caret equal to c. So this defines a function which is r square maps to r, that is real to real. F of xy is ax minus by. Okay. So now our problem is to decide if there is a real solution to the equation f of xy equal to c in the triangle P. So I have just plotted here this f of xy. Okay. So you see here x axis, y axis, and there is a line y is equal to x plus epsilon. Okay. The solution lies in this UVW triangle. Okay. In the triangle P. This is triangle P, UVW. Okay. So we should have minimum xy belong to P, minimum of fxy, xy belong to P should be less than equal to C, less than equal to maximum xy, x comma y belong to P, fxy. Now there is a lot of mathematics, but I will just give the results of this. So we have a plus we define as equal to max a comma 0 given two integers. Given an integer, a plus is simply max a comma 0. Suppose a is 3. So max of 3 comma 0 is 3. A plus equal to 3. If a is negative, so minus 3 comma 0, max is 0. So a plus equal to 0. A plus is equal to max a comma 0 and a minus equal to minimum minus a comma 0. That is how I define a plus and a minus. Okay. So this is let a, b, p, q, epsilon denote real numbers such that p less than equal to q and 0 less than equal to epsilon less than equal to q minus p. The minimum and maximum values of the function f xy ax plus by in the right triangle P defined by the inequalities P less than equal to x comma y less than equal to P and x less than equal to y minus epsilon are given by the expression that I have given here. It is a complicated expression where a minus minus b को उसका plus value. This is given in that Banerjee's book. The total derivation is beyond this lecture. So we can simply use the result. Okay. So bounds test. So we are interested in bounds test. Suppose that a variable x ai plus a0 of statement s and a variable x bp bi plus b0 of a statement t cause a dependence between s and t in the loop, and let q caret be equal to q minus p by theta and c is equal to whatever right hand side of that expression. If s is less than t and t depends on s, then mu a comma minus b comma 0 comma q caret comma 0 less than equal to c less than equal to b a comma minus b 0 q caret 0. Okay, slightly difficult. If s equal to t and s depends on s, then this expression must hold. And if s less than t and s depends on t, then this expression must hold. Mu minus a minus b comma a comma 0 comma q caret comma 1 less than equal to c less than equal to V minus B A0 Q caret. Okay. Now this mu is defined on the next slide. So what we have to do is just substitute the values of A, B, P, Q, epsilon, and is just evaluate the right hand side. That will simply give you right mu values. Okay. So let's take an example. I equal to 10 to 200 in steps of 5. 7i plus 2 here, and in T, S is coming before T in the physical code. P10, Q200 and theta 5. Q caret is equal to Q minus P by, which is 38. Okay. So A is equal to 7. This A0 equal to 2. B is 3. B0 is 17. GCD of 7 3 is 1. Theta is 5. ये तो minus 25 अभी हमने किया. So since C0 is an integral multiple of theta GCD AB, GCD test passes, so there may be a dependence, but it may be outside bounds. So therefore now we have to apply bounds test. So T delta L, T depends on S, as delta T becomes mu 7 minus 3, 0, 38, 0. Okay. So we can, I'll just mention how it has come. ये है ना, A minus B, T depends on S कर रहे हैं अपन या क्या कर रहे हैं? Let me check. Where T depends on S. So first expression. We want to check whether T depends on S. So A minus B 0, Q caret 0. A minus B 0, A minus B 0, Q caret 0. B is 3 and A is 7. So A minus B 0, 0. Less than equal to C. C is minus 5. Less than equal to V, which is again A minus B. Go back slide. A minus B 0. Acha, wo same. But A, mu and V are इनका expression is not exactly same. Either min है. In the first expression there is min of b comma a plus b comma 0. In the second it is max of b comma a plus b. So their values will differ. And then solving this, so compute the values of mu and v functions, and we get minus 114 less than equal to minus 5 less than equal to 155, which obviously works. So there is a dependence of t on s. Okay, it may exist. Okay. So what is that? If either one of the two tests, GCD and bounds test, does not succeed, then there is definitely no dependence. Then there is definitely no dependence. If both the tests pass, then we assume there is a dependence. The situation rarely arises where both tests are passing and dependence does not exist. That can happen, but that possibility is very rare. Okay, so shall we stop, Rajesh?
Yes, sir. So
Dependence analysis I have.
yeah.
So
Yeah,
open
yeah.
to
Okay.
question के लिए 10 minutes for
Right,
questions. Okay.
Right, sir. So participants have any questions, please ask, sir. Hello.
Hello.
So if the participants have any question, kindly put into a chat window or simply ask, sir.
हाँ, दोनों तरफ कर सकते.
Yeah, yeah.
खरे तू वॉज ओपन एमपी नाही का याच्यात?
उद्या टुमॉरो.
अच्छा, टुमॉरो
उद्या
ओपन एमपी.
ठेवलेलं
ओके.
आहे. या, या.
हा, ठीक आहे, ठीक आहे.
If there are no any questions from participants, then we have to conclude it. ठीक ना सर?
हा, ठीक आहे ना. ओके.
So I would like to thank Satya sir for presenting a brief on multi-core architecture, also on parallel processing by using a different code, and also explain dependency analysis by using some program fragments, and also explain application areas of parallel processing and techniques of parallelization. So thank you, sir, for your nice presentation.
Okay.
And also thanks for accepted our invitation for delivering a talk on dependence analysis. Thank you, sir.
चलो, ठीक है. Okay.
Thanks to all participants, and tomorrow morning 10 o'clock start our session on OpenMP and OpenMPI.
कोण घेत आहे रे?
And yeah. 2 sessions on OpenMP and MPI, and 1 session is on life management.
नाही, वन सेशन ऑन
Life management, as far as the suggestion from AICTE.
लाईफ मॅनेज.
Life management, that is the motivational.
अरे बाप, घेत आहे. हु इज टेकिंग दॅट? ठीक आहे. ओपन एमपी कोण घेत आहे?
सर नाही, ते या एक मॅडम आहेत, मोटिवेशनल टॉक देतात त्या. काय नाव तुमचं? ती UAE आहे. ओपन एमपी कोण घेतो? हा. आणि सर ओपन एमपी MPI जितेंद्र घेतोय.
अच्छा, अरे वा, जितेंद्र का? ओके, ओके.
2 सेशन त्याचे ओपन एमपी आणि MPI ला ठेवलेले आहेत. जितेंद्र
अच्छा, 3 सेशन घेता येतो? बापरे.
2 सेशन.
ओके, ठीक आहे. चलो, ठीक आहे. बढ़िया.
Okay, sir. Thank you. Thank you, sir. Thank you all the participants.